Hello, I am Spoon, and in this video, I will be going over 3 practice problems that I made up on my own based on somewhat real-life scenarios to show different ways of solving systems of linear equations. And without further ado, I will be going over the first problem, which deals with a hummingbird feeder. So in my backyard, there is a hummingbird feeder with nectar inside. And hummingbirds will fly by, they'll hover above a fake flower. There's a hole in that flower where they can stick their tongue in to drink up the nectar. This nectar we make on our own, and it has to follow a specific formula. There needs to be 4 parts water to every 1 part sugar. So let's say water is defined by W. And let's say this is a capacity in units of milliliters. And S equals sugar, which is in units of milliliters. So this means W divided by S needs to equal 4 in order to follow this ratio. Now let's say, what is the amount of water and sugar I need for 100 milliliters of nectar? So let's write a system of linear equations. The amount of water and the amount of sugar should add up to 100 milliliters. And if I rewrite this by multiplying S and then subtracting, I can say that W minus 4S equals 0. And this would be in units of milliliters. So I have a system of linear equations. I have 2 unknowns, which is the amount of water and the amount of sugar. And with 2 equations, 2 unknowns, this means that this can be solved. And these equations are linearly independent, so I can't add or subtract them in a way to get another equation. So I can't just multiply this top equation by a constant to get this equation down here. And I can't add them. Well, there's only 2 equations. There's not a whole lot to add together. In any case, let's solve this equation. And I'm going to use substitution. So going back to this equation here, I'm going to rewrite it as W equals 4S. And let's actually call this equation 1 and equation 2. So I'm going to take equation 1. I'm going to make sure that all W's are equal to 4S. So I'm going to write W, which is actually 4S, plus S equals 100 milliliters. That is equal to 5S equals 100 milliliters, divide both sides by 5, and now S equals 20 milliliters. So now I have a solution for the amount of sugar, but how much water do I need? If I use equation 1 again, and I have this substituted in, that means W plus 20 milliliters equals 100 milliliters, which means W, subtract both sides by 20 milliliters, equals 80. All right, I have my solutions. Let's double check. W, which is 80, plus sugar, which is 20, equals 100. That is correct. 80 minus 4 times 20, which is overall equal to 80. 80 minus 80 equals 0. So these are the correct solutions in order to make sure I have the correct ratio of water and sugar and the desired amount of solution. So now I can make 100 milliliters of nectar for this feeder. Sorry, I put my head over the eraser icon, which means I accidentally opened Zoom. All right, let's go to another problem. This time I won't immediately solve it with substitution. So let's say I have a restaurant. I'm gonna have a big sign on front that says restaurant in my beautiful handwriting. I have my doors, yada, yada, yada. Now, the maximum occupancy of customers inside the restaurant that can be seated is 50 people. Or let's just say I want to have 50 people eating at once in this restaurant. I also have 9 sets of table decorations. Let's say I also have plenty of chairs. So I don't have to worry about getting a bunch of chairs to seat 50 people. I already have them. I also have access to circular tables that can seat 8 people, rectangular tables that's giant, rectangular tables that can seat 6 people, and then square tables that can seat 4 people. These table shapes are not to scale. Um, I have 9 sets. And for a final thing to mention, I want there to be twice as many square tables as there are rectangle and circular tables. So let's say the number of circular tables is represented by a C, the number of rectangular tables is represented by an R, and the number of square tables is represented by S. So I want the amount of square tables to the amount of circular rectangle tables to equal 2. Just to give a little bit more uh, storytelling to this problem, square tables are nice because you can stack them together to make a larger table, and also square tables on their own seat the least amount of people. However, it's good to have larger tables because just combining square tables can sometimes make a lumpy surface. I hope you're really engaged in this problem now. So with all this information I've given, I can start writing a system of linear equations to try and make sure I know the amount of each table that I want. So first off, let's address that I want 50 people to be able to be seated, no more, no less. So I could write 8C plus 6R plus 4S equals 50. That addresses this. Now I want to have, let's deal with this. So I can rewrite this as negative 2C minus 2R plus S equals 0. And this addresses that I want twice as many square tables as other table types. So let's write negative 2C plus minus 2R plus S equals 0. So this deals with the ratio. And finally, I have 9 sets of table decorations. And so I need to have 9 tables. So C plus R plus S equals 9. Now I have my system of linear equations. I have 3 unknowns and I have 3 equations. You can't add them together or multiply or whatever to get a repeated equation. For instance, I can't take this equation by here, multiply it by a constant A, add it to this equation here, multiply it by constant B in order to get this problem. If the system of equations are not linearly independent, then when I go to solve this problem, I will find I have an infinite amount of solutions. But for this case, there is only one solution per variable. So let's define this as equation 1, this as equation 2, and this as equation 3. Let me just kind of delineate this. All right. Instead of doing substitution this time around, I'm going to add equations together to try and isolate. So I want to, it looks like I can easily isolate this S out in these two instances, because if I multiply equation 3 by -2, so let's say -2 times equation 3, and I add it to equation 2, I'm sorry, just multiply by a 2, not a -2. This will cancel out this 2c, and this will cancel out this r, and then I'll be just left out with the variable s. So looking to variable c in both equations, 2 times c here plus a -2c above in equation 2 equals 0. So I have 0. Then looking to the r's, negative 2r minus 2r. Make sure to pay attention to this negative sign here, or subtraction operator. Those cancel out, and so I have 0. Then I have 2s, add it with this s here, I get 3s equals, now I have to multiply equation 3 by 2, which is 9 times 2, 18, and add it to equation 2, that's 0, so it's still 18. So now I have this equation, which is equal to 2 times equation 3 plus equation 2. This is convenient because it's just s, and s equals 6 if you divide both sides by 3. And now I have s equals 6. Now, in this case, I'm going to use substitution. I'm going to take equation 1 and rewrite it as, let's just say, equation 4. I'm going to use s equals 6 and incorporate it, and then I'm going to subtract this product over here. So 4 times 6 is 24. 50 minus 24 equals 26. And I have on this side 8c plus 6r. Now I'm going to try and extract out, let's say, variable c. And I can do that if I take equation 2. I'm going to multiply it by 3. And I'm going to add it to equation 4. So in equation 2, 3 times -2 equals -6. I'm going to add it to 8, which gives me 2. So then I have 2c. Let me just kind of barrier this off. Then for r, -2r times 3 is then -6r. Add it to 6r down here, and I get 0. And then finally, with regards to s, I have s here, multiply it by 3. And in equation 4, there is no s variable, so I don't have to worry about it. So now I just have 3s. And then for the right side of the equal sign, 3 times 0 equals 0. And add that to equation 4, which is 26. Now, since I already know s equals 6, I can just simplify this very nicely. 3 times 6 is 18. 26 minus 18 equals 8. So C now equals 4. All right. The only unknown is R, and that is really easy to find if I do substitution for equation 3. So C is equal to 4 plus R plus S is equal to 6. And this all equals 9. Now, if you solve this, then you get R equals -1, which you may realize, what on earth does -1 rectangle tables mean? Doesn't make sense to this problem. Let's just make sure we can double check that everything is correct. So in equation 1, you have 8 times 4 plus 6 times -1, which is 6. Oh, wait, let me just write it all out. 6 times -1 plus 4 times 6 equals 50. So this is 32 minus 6 plus 24 equals 50. 32 minus 6 equals 26. 26 plus 24 equals 50. So this solution satisfies equation 1. For equation 2, -2c, so that's -8 plus 2 plus 6 equals 0. That is correct. In equation 3, remember equation 4 we kind of just made up later. It's a combination of equations 1 and 3, so we can ignore that. So going to equation 3, 6 plus -1 plus 4 does equal 9. So yes, our solution is correct. It's just in this instance, our solution, even though it satisfies all of these equations, doesn't make too much sense. However, it's kind of close to what we want. So let's say we have S equals 6, C equals 4, R equals 1. What if I just, oh, sorry, R equals -1. I'm just gonna add 1 here, and I'm gonna subtract 1 here. So that I'm just modifying my answer a little bit so that S equals 5, C equals 4, and R equals 0. So if you look into equation 3, this solution is satisfied. That matches the 9 sets of table decorations I want to use. So 3 is all good. Then let's look to equation 1. 8 times 4 equals 32 plus no rectangles plus 4 times that. So this equals 48. And then finally, sorry, equation 2. -2c, that is -8, minus 0 plus 5 equals -3. So these solutions are kind of close, not quite, but it is a more real answer. Alternatively, I can just, I previously had this solution 6 or -1. What if I just add 1 here and then I subtract 1 here? So that my final answer is then 6 squared, 3, 0. So I'd have 24, this is for equation 1, plus 24 equals 48, then -2c, that's -12. I'm sorry, -2, uh, that's -6 plus 6 equals 0. And then 6 plus 3 equals 9. Yeah. So this solution here best fits my criteria while giving an answer that makes sense. So in this problem, I'm mixing linear algebra with also some, I guess, critical thinking skills. Um, I think maybe in the real world, it'd just be good to guess and check, but we did take a more analytical approach. In any case, with regards to this video, I used a mix of substitution and adding equations together. So we're kind of building off the last problem, which used substitution, but increasing the complexity, especially since we have three unknowns. All right, we did two problems, one more to go. Now, I originally was going to try to make this a physics problem on Earth, but gravitation due to acceleration on Earth near the surface is around 9.81 meters per second squared downward. 9.81 is not a nice number, especially if I'm doing math by hand. And so we're going to the planet. I made it up. It's called Zobar, and they're home to the Zobarian people. Here are some Zobarians, and these Zobarians are doing a sort of competition. Let me move them down a little so I can draw more. They're trying to figure out who can throw a ball the highest. So there's one Zobarian here. This guy's record is 18 merflops. Merflops is the unit of measurement on Zobar. So this guy throws a ball, it just makes it over this tree and goes a little bit higher and then comes down. This guy says, uh, he was, this guy is saying, I beat your record. And this guy down here, whose record is 8 merflops, says, nah, ah. So then they decide to use some system of linear equations to figure out who's right. So in a constant gravitational field, projectiles take a parabolic path. A parabola is defined. Oh gosh, I did it again. I touched my video. All right, I'm going to move my head here. Oh, that's too much. So a parabola is defined by a function ax squared plus bx plus c. So x is a horizontal coordinate, y is a vertical coordinate, and a, b, c are constants. Let's say that both Zobarians agree that the ball was initially thrown off the ground one merflop above the ground. And let's say this axis here is x equals 0. So our first data point is 0, 1, meaning the ball was initially thrown by this Zobarian here, 1 merflop off the ground. Now, 5 meters away is a Zobarian tree. The ball just got over it along its parabolic path. So it's another data point, 5 merflops away, and they both agree that the tree is 16 merflops tall. Now for a final data point, the ball hits the ground 20 merflops away. So our final data point is 20 merflops away. It reaches the ground at 0 merflops. So the question is, did this Zobarian exceed 18 merflops at its highest peak. So we're going to figure out what the constants are of this parabola, and then we're going to find the vertex, which is right here. Unfortunately, we're not just going to use linear algebra to solve this. We're also going to have to complete the square of the final equation. But let's worry about that later. We have our data points, and so let's create our system of equations. So for the first data point, x equals 0 and y equals 1. 1. That means we can write x squared. Just for clarity, let me write it like this, equals y. So same equation, I'm just moving y to the other side. If x equals 0, then we can forget about a and b. C remains the same, and y equals 1. Now for our next equation, x equals 5 and y equals 16. 5 squared is 25, so we can write 25a. Our next thing, x equals 5, so we have 5b. C does not change, and this is equal to 16. And then finally, our last data point, x equals 20 and y equals 0. So 20 squared is 400, a, plus 5 times, oh, I'm sorry, 20 times b, because x equals 20, plus c equals 0. So now we have our system of linear equations. Now, I could do this by hand, but I want to do a different approach for each problem. So instead of that, let us use something called reduced row echelon form. We kind of did that before with this problem where you add equations together, but we're going to have a calculator do that for me. So first we got to set this up for the calculator. And we're going to do that with matrices. If you don't know what a matrix is, instead of having a variable equal one value, what if it was equal to multiple values? What if it was equal to this? What if another was equal to this? Matrices can be added together if they're same size. For instance, if I had C equals 4, 3, 2, 1, I could do A plus C, just add together the corresponding entries, and that just equals 5, 5, 5, 5. With multiplication, the matrices don't have to be the same size. If they are the same size, they must be squares. If not, the columns of the first factor must be equal to the number of rows of the second. And that matches for A and B. Because when you multiply matrices, you multiply and add along the rows of the first matrix and then along the columns of the second. So you multiply this way, and then there's only one column for the second, so it'd be that way. And the way it does is you multiply the first term along each direction and then add it to the product of the second. So this is equal to 1 times 1 plus 2 times 2. And then do the same for the next part. 3 times 1 plus 4 times 2. That gives you a solution is equal to 5 and 11. So that's kind of how matrices work. There's a lot more things to think about, like what is the inverse of a matrix, other properties of matrices. But for this video, you just got to know multiplication. And so we can write this system of equations as matrices being multiplied together. So let's say we have matrix A is equal to the numbers that each variable are being multiplied. So it'd be 0, 0, 1, because 1c, then 25, 5, 1, 400, 21, then our, let's say z, let's say ABC is equal to z. So we have our constants ABC as this column vector, which is a type of matrix that only has one column. And then this is all equal to 1, 16, 0. And so A times Z equals B, which can be written as 0, 0, 1, 25, 5, 1, 400, 21 times A, B, C equals 1, 16, 0. At this point, it kind of looks like a really complicated way of saying the exact same thing, but it is useful. And just to double check, this system of equations and this system of equations are the same because 0 times A plus 0 times B plus 1C, that's here, equals 1. And the same goes for each row, 25 times A plus 5 times B plus C times 1 is equal to 16 and 400, etc., etc. But wait, there's more. You can represent the system of linear equations as an augmented matrix. So finally, I'm just going to write 0, 0, 1, 25, 5, 1, 400, 21. I'm going to have a bar here to indicate the last column of this augmented matrix, 1, 16, 0. So this represents our a set of linear equations. And you could add multiples of rows together to isolate different variables, which is basically what we did here. So I could like multiply this row by, I don't know, -1, add it down to here, then you would get rid of this variable. And in the end, you want something that looks like an augmented matrix in which the left side looks like this, and the right side equals some numbers. If you have this, then this number is equal to A because this corresponds to this spot. Oop, this spot here. That'd be 1 times A equals this number. Then this would be B, and this would be C. And this sort of formatting is useful to do by hand. It just saves space. But it's also the formatting you can use to input into a calculator. You can do this in a TI-84. You would just have to enter the matrix. You might go to like alpha zoom or alpha F3. It'll ask for the amount of rows and columns you want in the matrix. You input all the numbers, then you find the reduced row echelon form of that matrix, which is this form down here. And that operation can be found by going to second X inverse or second matrix, go to the math column, go all the way down, and you find under item B, RREF, which stands for reduced row echelon form. I verbally set this out loud. Maybe it's hard to follow if you don't have your TI-84, but let me show you how it works if you use coding. So I can only share one screen at a time as far as I know. So try to remember this matrix representing our system of equations so we can find the shape of the parabola and then later determine how high this ball actually went. So I'm going to stop sharing my iPad screen, and then I'm going to share my code. All right. At this point, I don't think you can see my face anymore, but you should be able to see uh, my environment in Octave through Visual Studio Code. So here is the matrix that I showed earlier. I could also have expressed it as a through this kind of delimitation. Colon, semicolon corresponds to the next row. I'm not going to do that because it's going to take a while. But anyway, I have the matrix here. And then here is the function RREF, which is reduced row echelon form, which then will create an augmented matrix, which is nicer to read. So I already have the output here. Let me just run this code. And you'll see I have this side of the augmented matrix, which is the diagonal of ones, and then I'll have my numbers here, which correspond to A, B, and C. So let me write this down on my iPad real quick. I'm going to, I gotta erase a few things to make space. So let me write down this augmented matrix, which has the diagonal of ones. And then I'm going to round that first number to negative 0.2. I'm going to round that to 4. And then I'm going to round that last number to 1. All right. Now I'm going to stop sharing my screen and I'm going to share my iPad screen once more. You can also do this in Octave Online, MATLAB, Wolfram Alpha, other coding languages, but they all should do the exact same thing. All right, I'm sharing my screen again, and now you should be able to see my face. Here I am. And I have the augmented matrix here. And this shows that A is equal to negative 0.2, B equals 4, and C equals 1. So now we have our defined parabola, negative 0.2x squared plus 4x plus 1. And that is the shape of the parabola. Now we are in the not linear algebra side of things. Let me complete the square. You know what? Maybe I'll save you time. Negative 0.2 x, let me think about it. Minus 10 squared plus 21. Oh wait, yeah, I gotta show my work so that you believe me. Of course, if you're taking a test, it's good to show work unless it's a multiple choice test and they don't care if you show your work. So the way I did this is negative 0.2, that's x squared plus, oh, minus 20, x plus 1. I want to complete a square, so then I'd have x minus 10 squared, which means then I'd have to add 100, 20 on this side. This is 21. Yep, there's 100 times -2. Perfect. Yep, okay, that's right. That means based on completing the square and having it in vertex form, the vertex is at 10, 21. So that means this Zobarian right here is correct. They were able to throw the ball that high up, beating this Zobarian's record of 18 Murflops. Thank you so for much. Thank you so much for going through this problem with me. It's complicated, but I just showed you uh, a part of linear algebra, and I have used this a lot in my research to solve systems of linear equations, whether it's for X-ray diffraction or fitting curves to data points. But that completes this video. In the first question, we solved for finding what we need to make a solution of Hummingbird nectar using substitution. Then we used substitution and adding equations together to figure out how many tables we need for my restaurant. And then we helped handle this Zobarian dispute using basically this, except in a different notation. I really hope uh, this isn't lagging too much for you. But in any case, yeah, I hope you enjoyed these problems and get to see how systems of linear equations can be used in the real world. And now you know different ways of solving. If you understand how this all works over here, you're probably going to solve real world problems with this because it's much faster than doing things by hand. But otherwise, this all here still works. And if you're doing a test, you might need to show your work. So thank you again. I hope you have a great day and have a better understanding how to solve systems of linear equations and have enjoyed this little introduction to linear algebra. Uh, have a great day.